All right, 2.4, continuity and discontinuity. Your essential question, how do you define and use continuity? And I've just copied this image from page 46. And there's a whole bunch of different types of discontinuities that we've already talked about. So the first one is removable discontinuity. That's where you just have a hole and you have no value for C. So f of C is undefined. Okay, so no f of C. Yeah, let's go ahead and highlight that. Why not? All right, you have another type of removable discontinuity where f of C is some value. You still have a hole, like the function itself is not continuous, right? There's a hole in that function, which means that, you know, the limit as f approaches C from the left and the right is L, but f of C itself is something completely different. So in this removable discontinuity, f of C is not equal to the limit as x approaches C. Okay, then you have the step discontinuity. This one's really obvious because it looks like a step. And basically, you know, the limit from the left is not going to be equal to the limit as you approach C from the right, so you don't have a limit. The limit does not exist. Okay, then you have vertical asymptotes. Anytime you have this vertical asymptote, you're not going to have a continuous function. And they call this an infinite discontinuity because, for example, on this side it's approaching infinity and on this side it's approaching infinity. That would be true as well as if you had this side maybe approaching infinity and then maybe this side was going down and approaching negative infinity along that vertical asymptote. Either way, they call it an infinite discontinuity. Now this is not, I should say, there is no limit on an infinite discontinuity. Okay, there's also no f of C. It's not defined. The function is not defined at C. This is continuous. It's kind of a bad graphic because we're talking about types of discontinuities. This is a continuous function, and so is this. So the problem with this function here, and you'll learn this later, is this cusp. So a cusp, and we'll define a cusp in a little bit, but this cusp is still continuous. It just makes this like point. So later on you'll see we can't do some types of calculus with this, but it is in fact continuous, okay? So this is continuous and we call this a cusp. Okay, this is a continuous function. And the limit as x approaches C will be equal to what the value of f of C actually is. Right, so the limit from the left and the right are approaching f of C, so that you do have that limit, and then f of C is also going to be whatever that limit is. Okay, so the limit is equal to f of C. And then this is just a function that is continuous. This is what your normal curves look like without any discontinuity. So, you know, you can define f of C, and it's also the same as the limit. So again, the limit is going to equal f of C. All right, so let's define continuity. I've actually given you two definitions here. So the first definition is continuity at a point. Okay, so how can we either visually or algebraically figure out if a function is continuous at a point, any point that we choose here? Well, first of all, f of C has to exist. And the limit as x approaches C of f of x also has to exist, right? So that means that this means that you have both the left and the right limits equal to each other. So maybe we should write that down. So this means the limit as x approaches C, I should say from the left of f of x will equal the limit as x approaches C from the right of f of x, right? So those left and right hand limits have to be the same, which means that your limit does in fact exist. And the limit as x approaches C of f of x has to equal what f of C actually is. So you can see this one's continuous. F of C in fact does exist. The limit as x approaches C also exists, and the limit's the same as f of C. So it in fact checks off all three of these requirements. Now, if we want continuity on an interval, Well, continuity on an interval isn't, I mean, I don't know how important. To me, it's more important to make sure that every point within that interval is basically continuous, okay? So that's really what continuity on an interval is. Function f is continuous on an interval of x values if and only if it is continuous at each value of x in that interval. So basically for every single point in that interval, this top part must be true. And then it's continuous on an interval. So when I was using this example here, I checked just point C. Well, if I wanted to see if it was continuous from, let's say, x equals 0 to x equals 20, I'd have to check the continuity of every single point between x equals 0 and x equals 20. Now, only one-sided limits need to equal the function value, because at the endpoints, so for example, let's call this x equals 20. There's no function that keeps going here, right? So we're going to assume that we're just talking about this interval. So I have no idea about what the right-handed limit will be. I only can tell you what the left-handed limit will be, because there's just nothing over here. The function basically ends. Okay, so I wouldn't focus too much on that. We're really going to focus on making sure things are continuous at specific points. That's usually where it gets a little bit confusing too on your calculator. Like, you can't actually see if it's continuous. You don't know if there's a hole there. So there's things that you can do to check. So this is where I'll define a cusp for you. So remember, the cusp looks like this. It's basically like a sharp point. Okay. So a cusp is a point on the graph at which the function is continuous, but the derivative is discontinuous. So you don't know enough about derivative. Derivative basically is instantaneous rate of change, or slope, and we'll get to that. But basically the derivative, if the derivative is discontinuous, you're going to have this cusp, because, so right now just think of derivative as slope. The slope on this side of the cusp leading up to C, right? So the limit, or I should say the slope, as we approach C from the left, is positive. But what is it on the right, right? So as we approach C from the right, notice this is a negative slope. So the slopes are unequal, which means that the derivative is discontinuous. I don't want to worry too much about that right now. We'll get more into that, I promise. But a cusp is a sharp point or an abrupt change in direction, basically. So think of it as that. Sharp point or a corner or something like that. An abrupt change in, again, if you approach that cusp from the left and the right, you're going to have different slopes. Okay? I'm just reminding you here of your one-sided limits. This is basically the limit notation as I used over here on the front page, right? But this is basically your left limit notation and your right limit notation, okay? And this was in your last notes too. And then we're going to do some examples. I gave you guys this exploration in class, and this is what we're going to work with, okay? So we have our piecewise function here. K is some constant. We're going to plot the graph of f when k equals 1. Okay, so we're going to sketch that result. Now, hopefully you can do this without your calculator. I'm hoping that this would be pretty simple. And I'm looking at my domain here. I know that this piece is going to be when x is less than 2, and this piece is going to be when x is greater than or equal to 2. So the two graphs break apart, or the two pieces break apart at x equals 2. So I'm going to put 2 on here for sure. And this is probably going to need to go a little bit further. I know this needs to go a little bit further because I'm looking at this right here and I'm saying, hey, that's an x squared graph that's been moved to the right 5 units. All right, so starting with my first piece, x does not equal 2, so there should not be a solid dot on this graph at x equals 2. But this is just a linear function, y equals x plus 1, where my y-intercept is 1, and my slope is 1. So I'm going to go up 1 over 1. And then I can even go up one more, it's 3 here. If I go up one more and over one more, that's going to put me at x equals 2, so I need to have an open circle. Something like that. And then the other piece, now they're saying when k equals 1, so that way it'll be easy for us to graph. So the coefficient here, or the constant coefficient, is 1. Okay, so this is going to move over 5 spaces, so I know my vertex of the parabola is going to be here. It would be really helpful if I knew what the value was when x equals 2, right, because x does equal 2. So I plug 2 in there and I get negative 3 squared. Oh great, that's 9. I wasn't quite prepared for that. So we're going to need to go a little higher. Okay, so at 2, when I plug 2 in, I get 9, and x equals 2 here. So I plug 2 in, I get 9. I know it's a parabola, so it's going to be, my axis of symmetry is here at x equals 5. So if I go 3 spaces to the right, right, because it's 1, 2, 3 spaces to the left, so 1, 2, 3 spaces to the right, I'm also going to be up at 9. So it's going to look something like this. You can plot more points if you want. And it's going to continue on after that. So obviously, function f is discontinuous at x equals 2. And tell what it means for it to be discontinuous at a point. Discontinuous at a point. So that takes us back to that definition of continuity at a point. Okay, so looking back at the definition of continuity at a point, first of all, f of c must exist. So if we're talking about discontinuous, then f of c would not exist. Second, the limit has to exist. So if we're talking about discontinuity, then the limit would not exist. And then 3, and that would mean that basically the left and the right limits are not the same. And then 3, the limit as x approaches c of f of x would not equal f of c, which basically is the very last thing to make it discontinuous. Okay, so let's fill out our exploration. So tell what it means for a function to be discontinuous. We can say a function is discontinuous when 1, f of c does not exist or is undefined. 2, the limit as x goes to c of f of x does not exist. And that would happen because the limit as x goes to c from the left of f of x does not equal the limit as x goes to c from the right of f of x. Hopefully you know this. This was on your test. Chapter 1. Okay, and then 3, basically the other part would be that the limit of this does not equal what the actual value at c is, the actual output value at c. So the limit as x goes to c of f of x is not equal to what f of c actually equals. Okay. All right, next we're going to actually find the limit of as x goes to 2 from the left and the limit as x goes to 2 from the right. Okay, and the second limit will be in terms of k, because remember, in our original problem, there is a k being multiplied to the second piece, okay? So the first piece is when x is less than 2. So it's everything to the left of 2, right? So this means that I am approaching 2 from the left. Okay, so I'm going to use that first piece. And then for the second piece, the limit as x approaches 2 from the right, well, that's this piece, right? Because I'm coming to 2 from the right. What's my output going to be? All right, so then I'll use proper notation. So the limit as x approaches 2 from the left of f of x is basically going to equal the limit as x approaches 2 from the left of that first piece, x plus 1. Okay, and if I plug 2 in, do I get something out? I do. Nothing's undefined there, so I can just plug it in. It's really just going to be 2 plus 1, which is going to equal 3. Okay, and then the second part from the right, the limit as x approaches 2 from the right of f of x is basically going to equal the limit as x approaches 2 from the right of that second piece, which is k times x minus 5 squared. Okay, and when I plug everything in, I still have a k, and then I have 2 minus 5 squared, which gave us 9, right? So this piece equals 9k. Okay, so that's the first part. What must be true of these two limits for f to be continuous at x equals 2? What must be true for it to be continuous at x equals 2? So which piece of this is important for both the left and the right limits? Well, they must be equal, right, in order for them to be continuous. If we want them to be discontinuous, then they wouldn't be equal. So they have to be equal. They must be equal. Okay, so this piece here and this piece here need to equal each other at x equals 2 in order for it to be continuous at x equals 2. Right now, they're not continuous. I hope you all agree with that, right? There is a step discontinuity right here. So we are now going to find the value of k that makes f continuous at x equals 2. All right, wonderful. So we just said that those two need to be equal at x equals 2, right? So what we're going to do is we're going to set them equal to each other. 3 will equal 9k. And so now I'll divide both sides by 9 to figure out what k actually needs to equal. So k is going to equal 1/3. So I have a new piecewise function that I've just created. It is this. F of x equals the first piece, nothing's changed. And then the second piece, the k has changed, right? We now have a k. And then they want us to graph it. So what is this now going to look like? All right, so maybe I should have written it here so that we had it. I'm going to write it one more time, sorry. All right, so nothing's changed on that first piece. So when I graph that first piece, I should probably go a little bit further to the right. When I graphed that first piece, my y-intercept was 1. Use my slope to get another point. X equals 1. And then to get my next point at x equals 2, we use my slope one more time, but remember, it's an open dot, right? So this piece looks a lot like this. Okay, I still have the same function, I just have this coefficient, which is going to basically change this graph a little bit. So I'm going to go still graph it. I think my vertex will still be at the exact same spot. But now when I plug 2 in, let's see what this gives me. So 1/3 times 2 minus 5 squared. So that's still going to be 9. So I'm going to have 1/3 of 9. So that's going to give me 3. So at 2, my output is 3. And this piece, I can actually say, well, x can equal 2. So it looks like I need to fill in this hole. Okay, I know it's going to go down to 5. And it's also going to go over here. That's my axis of symmetry. So if I go over to 8, I should also have an output of 3. So that 1/3 coefficient here kind of makes this whole graph become fatter and shorter, right? Which will look something like this. Okay. So I'm going to write a note that my graph is on back. The graph in problem 4 has a cusp at x equals 2. What is the origin of the word cusp, and why is it appropriate to use in this context? This was in your book. The word cusp comes from the Latin word cuspus, meaning a pointed end. Okay, so cusp comes from the Latin word cuspus, meaning a pointed end. So why is it appropriate? Why is it appropriate for this new graph that we've just created? Well, what is this thing? It's a pointed end, right? Our graph has a pointed end, so it does have a cusp. So it's appropriate because the graph comes to a pointed end at x equals 2. Okay. Number 6, so suppose someone asks, is f of x increasing or decreasing at x equals 2? With k as in problem 4. So with the k that we have, the 1/3 that we got right here. How would you have to answer the question? What then can you conclude about the derivative of a function at a point where the graph has a cusp? So what's happening at this cusp? At x equals 2, is our graph increasing or decreasing? Hopefully you said neither. Right? It's not increasing or decreasing. So we can say at x equals 2, f of x is neither increasing or decreasing. So that means we have no rate of change there, right? So what can we conclude about the derivative of a function at a point where the graph has a cusp? If there's no rate of change, does the derivative even exist? So, and I think I've gone over this before in a previous video, but thinking about your rate of change here, well, as I'm coming from the left, I've got a positive rate of change, right? As I'm coming from the right, I've got a negative rate of change. So there is no one number that the derivative would approach. Right? So I can sit here all day long and estimate the rate of change from the left, and I can estimate the rate of change from the right, but it's not going to approach a limit for this rate of change. They're going to be approaching a positive rate of change and a negative rate of change. So there is no derivative. The derivative would not exist since it would have a positive rate of change from the left and a negative rate of change from the right. We'll just leave it at that. Okay, what did you learn as a result of doing this exploration that you did not know before? Hopefully you can figure something out to put there. So let's go back now and let me show you how to graph this in your calculator using Boolean variables. Okay, so that's what we're going to work on right now. All right, let's see, we got bright lights everywhere. What can I do here? How about that? That looks better. All right, so I'm going to graph two pieces of this function. One of them is going to be x plus 1, and the other one's going to be, for right now, k was 1, so we'll just do x minus 5 squared. I don't need that. Now here's the thing. You can make it restrict so that you're only graphing this piece up to 2. Okay, and then you're only graphing this piece beginning at 2 and moving forward. Okay, and the way that you do that is you basically divide out the domain. So you're going to divide this by, and put it in parentheses please, x, and now we need to do less than. So that is under the math num I think I lied. That is under second math, sorry. That is under, so you want the inequality, the less than sign, and that is under, if you hit second and math. So under second and math, that's where your less than, greater than, all those signs are. Just select it, put it in there, less than 2. Okay, and then I'm going to do the same thing for my second piece. I'm going to divide it, this time by x. Now again, to find your inequality sign, it's second math. And we're going to do this one greater than or equal to 2. I'm going to check my window before I graph this. I think I'm going to make my x max larger. How about 10? And let me make my x max smaller. Let's go negative 10. And my y min is also going to be negative 10. Look at how cool that is. Is that not awesome?
All right, and then you could do the exact same thing now for once we've made it continuous, right? You basically just divide out these Boolean variables, so these domains, okay? You just divide by it, okay? That's all under second math to get your inequality signs.
Now let's do some problems from the section. So we'll do page 50. And in our notes, I wrote that I would do with you 2, 4, 6, 8, 14, and 43. All right. So starting with 2 and 4, 2 through 8 actually even. Let's go ahead and look at these. So for these problems, we're going to state whether the graph illustrates a function that has left and right limits at the marked value of x, has a limit at the marked value of x, is continuous at the marked value of x. Okay, so we're going to use left and right limit notation, okay, to say whether or not there are limits from the left and the right. And then if the left and the right limits are the same, then we know that there's a limit at that value of x. And then we'll see if it's continuous, because basically it'll fall into, or it'll check off all three of these categories right here. All right, so let's go ahead and do that. Starting with 2. So when I look at 2, left and right limits, so let me just go ahead and write down the limit notation. The limit as x approaches, and am I just going to 3? Yep. From the left of f of x equals something, and the limit as x approaches 3 from the right of f of x equals something. So let's see, this is A. So the limit as I approach 3 from the left appears to be some number. We'll call that f of 3. Okay, and then as I approach it from the right, it's the exact same value. Okay, so I'm going to say both of those are equal to f of 3. Oops, I'm off the screen. Okay, B has a limit at the marked value of x. Yep, the limit does exist, right? So give me 1 second. Let's see how. So because the limit as x approaches 3 from the left of f of x is equal to the limit as x approaches 3 from the right of f of x, then that means that the limit exists. Okay, and then for C, okay, does it now hit all three of those check marks? Let's see, where did I put that? Oops, it's on the floor. 1 second. Does it then hit all three of these? Okay, well, we know that the limit exists. Okay, but does f of c exist? So let's look at that. So does f of 3 exist? Well, since f of 3 does not exist, right, f of 3 is undefined, there's a hole there, there's a removable discontinuity. Okay, so I would say something like f of 3 does not exist. Therefore, so it doesn't, right away, it doesn't even hit like the very first requirement, right? So right away we know it's not continuous at that point. Therefore, it's not continuous at x equals 3. All right, let's do another one. So for 4, so the first thing I'm going to do is the limit, and this one looks like it's going to -5, right? That's the marked value of x. So I'll do the left and the right limits. The limit as x approaches -5 of f of x, and the limit as x approaches -5. Oops, I should say from the left and from the right of f of x. Okay, so it looks to me like they are both approaching the exact same output. I'll just call that output f of -5 because there just happens to be one of them. Okay, so B, does it then have a limit? Well, if the limits are exactly the same, then the limit does exist, right? So the limit as x approaches 5 from the left of f of x is equal to the limit as x approaches negative 5 from the right of f of x. Therefore, the limit exists. And then the last one, is it continuous at the marked value of x? So once again, we're going to have to go through these 3 checkpoints to make sure that it actually does exist. Okay, so let's check for f of c. Well, f of negative 5 actually appears to be f of negative 5, right? It appears to be the exact same thing. Okay, so f of negative 5 does in fact exist. The limit also exists, right? So the limit exists. Negative 5 of f of x exists. And now the question is the limit and f of negative 5 exactly the same? They actually are, right? So we can say the limit as x approaches negative 5 of f of x is equal to f of negative 5. So f of x is continuous at x equals negative 5. Okay, so we hit all 3 of your continuity points for the definition, right? All 3 of those things actually occurred. And just by looking at the graph, you can see it's continuous. There are no removable discontinuities. There's no steps. There's no infinite discontinuities. Just by looking at 6, I can see that there's a step discontinuity here. That's not the marked value of x, so you kind of have to be, it's trying to trick you there. Okay, so the marked value of x is 5. Is it going to be continuous at 5? In fact, it is, right? We can see that f of 5 does exist, right? It's going to be whatever f of 5 is. I don't know. We'll call it f of 5. From the left, my limit is exactly the same as my right. Okay, it's all at f of 5. So therefore, I can see that it does exist. Okay, so we'll do that one real quick using our notation. So first of all, the limit as x approaches 5 from the left of f of x is equal to f of 5. And the limit as x approaches 5 from the right of f of x is also equal to f of 5. Okay, so therefore, the left and the right limits are exactly the same. So we know that the limit does exist. So I'll write that the limit as x approaches 5 from the left of f of x is equal to the limit as x approaches 5 from the right of f of x. Therefore, the limit exists. And then we'll check for continuity. So once again, looking at those 3 points for continuity at a point, yep, f of 5 does in fact exist. The limit does exist. And f of 5 is equal to the limit as x approaches 5. Okay, so f of 5 exists. Oops. The limit as x approaches 5 of f of x also exists. And the limit as x approaches 5 of f of x is actually equal to f of 5. So it is continuous. Pretty simple, hopefully. It's just really working with those definitions. Okay, let's do 8. Okay, so now it's just c is our x value. And you can see at c that the left and the right limits are not going to be the same. You can see that f of c does in fact exist at 6, right? But if because we have this step discontinuity, well, we know it's discontinuous. But I'll still go through the motions and I'll answer A, B, and C because it's good practice. So the limit as x approaches C from the left of f of x equals, and the limit as x approaches C from the right of f of x equals. Okay, so from the left, it appears that our output is, or our limit is going to be 8. And then from the right, it appears it's going to be 6. So this one's going to be 8, this one's going to be 6. So that means, is there actually a limit? Well, the right and the left-hand limits are different, so there is no limit. So the limit as x goes to C from the left of f of x does not equal the limit as x goes to C from the right of f of x. Therefore, limit does not exist. Okay, and basically if we know that the limit doesn't exist, then right there we know, well, if the limit doesn't exist, number 2 is not checked off for continuity at a point, so it's not continuous. So I'll say something like, since the limit does not exist, oops, how about f of x is not continuous at x equals C. Okay, what other problems did we say we were going to do together? 14 and 43. All right, so 14. So these are kind of fun. Sketch the graph of a function that has the indicated features. So 14, it has a value for f of -2, but has no limit as x approaches -2. So if it has no limit, that means that the left and the right limits are different, but it does in fact have a value for -2. So this is going to be something very similar to this, right? We did have a value for C, right? F of C, in fact, equaled 6. However, the limits were not the same from left and right, so the limit did not exist. Okay, so this time it's just going to break apart or do that step at -2. Did it tell me the value? No, it doesn't. Okay, so how about I just go, here's my value. Who knows what that is? You could make it up, but it's definitely got a value, right? Because oops, I'm not even on the page. I'm sorry. Okay, so there's -2. I just drew a graph, right, that went to -2. So from the left, my limit's going to be -2. Okay, that's going to be my output. However, I'm told that there is no limit as x approaches -2. So from the right, if I'm coming at it from the right, I need to have some other spot that it's approaching. And maybe this time I'll make it fancy. How about I do a curve of some sort? Ooh, look at that. And we'll call this, what do we say? It's f. Oh, maybe I shouldn't have put y then. I'll put f of x here. Okay, so there's a value for f of -2. It is whatever that output is. Okay. However, there's no limit because the left limit is equal to whatever that output is, but the right limit is equal to some other output. And we've got one more example. What did I write? 43. Okay, let's do 43 now. Because it's a pretty challenging problem to think about, so just in case if you're struggling, I thought I'd give you some help. So there's a picture which kind of describes the scenario. We've got a river, and there's a bridge that crosses this river. So let's see, so this will be my bridge. I'll just do this. We know that from one end to the other end, it's 120 feet. And Calvin has a couple of choices. So here's Calvin right here.
So he can cross the bridge. That's one option. And if he crosses the bridge, then we're saying that the bridge goes straight across this river, and therefore the angle at which Calvin is crossing this river is basically 90 degrees with the shore. So we can call his angle 90 degrees. And if he crosses the river using the bridge, his velocity with respect to time is going to be 5 feet per second. So that's one scenario. The other scenario is that he's in a rowboat, and now he crosses at some angle other than 90 degrees. So just to give you an idea, maybe it looks like that. Okay, where this angle right here, we'll call that theta. Okay, so we know that if he crosses using the rowboat, then theta is going to be somewhere between, well, in this situation, 0 and 90 degrees. But we can also take it to mean, maybe it's this angle here from the shore. So maybe it's the other end of 90 degrees. Maybe it's the upper end. So anywhere between 90 degrees and 180 degrees. And we know that his velocity when he crosses using the rowboat is 3 feet per second. And again, so looking at him in the rowboat here, this is him on the rowboat. We are not really sure what that distance is. I'll call that, well, what I'm going to do is I'm going to create a right triangle here. I know that this distance straight across the river at a 90-degree angle is 120 feet. I'm not sure what this is, but there's a way that I can figure that out, right? So I'll call this rowboat length, we'll just call that R. Okay, and I know the relationship between R, theta, and 120 degrees, hopefully. So I'm looking at this angle, I see that I have an opposite, I see that I have a hypotenuse. So I can write a relationship that describes the distance. Have to use a little bit of trig. But the distance here is basically going to be R, right? Well, I know that sine of theta will be my opposite over my hypotenuse, which is 120 feet over, oops, just dropped my book, over R. And therefore, if I wanted to solve this for R, basically multiply both, I can cross multiply, let's do that. We'll just cross multiply and then divide by sine theta. So I know then that R is 120 feet divided by sine theta. All right, so that's giving me a distance if I, or if Calvin takes the rowboat. Okay, what about the distance, just talking about if I just go, or if Calvin goes straight across this bridge? Well, hopefully you remember that distance is always equal to rate times time. And let's see, the distance here then is straight across, so it's 120 feet. His rate is 5 feet per second times time. Okay, and now I need to basically divide both sides by 5. So in order to do that, I'm going to do, 1 second over 5 feet. So 1 second over 5 feet tells me that the feet reduce, let's see, 5 goes into that 14 times, I believe. Ooh, 24 times. So I end up with time equaling 24 seconds on that one. Okay, going back to distance equals rate times time. For this one, I have my distance, which is 120 feet over sine theta. And we know that that's going to be 3 feet per second times time. So now I'll do the same thing I did over here, where I will get time by itself by basically multiplying both sides by 1 second per 3 feet. Again, the feet go away. Here I'm left with 40. So I've got 40 seconds over sine theta equals, let's see, time. All right, so let's see. So my final equation here, or my piecewise function, I'm going to make it a function of the angle that Calvin's journeying on. I think I'm going to run out of room right here. So I'm actually going to erase this and move over. Function of the angle, so whether he's going straight across the bridge or whether he's taking that rowboat. So it's going to be 24 seconds. It's going to take him 24 seconds if he decides to cross that bridge. So that's if theta is equal to 90 degrees. And then the other time it's going to take him is 40 seconds over sine theta. So this part's constant, this part's going to vary. So 40 over sine theta. Basically, if theta is not equal to 90 degrees, but we have to be a little bit careful with that because, you know, theta can never be 360 degrees. We're dealing with a bank here on the river, right? So if it's not 90 degrees, and if we want him to cross the river, it can't be 0 degrees. It can't be 180. It can't be 360, right? I mean, that's just going right back to where he started. So in order to encompass everything, we want to be somewhere between 0 and 180 degrees, but not including 0 or 180 degrees. So we're going to keep those two domains that I kept here, or that I came up with here. We're going to be in between 0 or 90 degrees, or we're going to be in between 90 degrees and 180 degrees. Okay, so when you graph this, because we worked in 90 degrees, we're going to want to make sure that we are in degree mode. So make sure you're in degree mode. And then we'll use our Boolean variables to deal with the fact that this one is only when x is going to equal 90. This one's going to be somewhere in between 0 and 90 degrees. You know, and if you think about it, if he's crossing the river over here, it's still between 0 and 90 degrees. Okay, so really, when we put this into our calculator, we only need to use the fact that we're talking about 0 to 90 degrees. It's going to give us the same answer here as well. Okay? Okay, so on my calculator, the first thing I'm going to do is put degree mode. Then I would go into my y equals. And I'm going to type in for my first one. It's always going to be 24 seconds. And I'm going to divide that. Oops, that's not dividing. I'm going to divide that by my Boolean variable, which says that x is always going to be equal to 90 degrees. I'm in degree mode, so I don't need to put a degree in there. And then for my second one, it's going to be 40 divided by sine of your angle. And in this case, my angle is going to have to be x. And then I'm going to divide that by my Boolean variable that says that I need to be somewhere between 0 and 90 degrees. Now, when I think about my window, the possibility of being along that bank tells me that I can cross the river at 1 degree all the way up to 179 degrees. So I'm going to make sure that when I graph this, I can't graph at negative degrees, that my max would be 180 degrees. Oops. Let's try that again. My x max for my degree would be 180. Not that it can even be 180 degrees, because then I'm just walking along the shore. And my y, let's see, we know it's going to take 24 seconds at 90 degrees. So it could be up to 40. I don't know. Why don't I go ahead? Let's do 100 anyways. Let's see what that looks like. Oops. Not for your min, though. Your min would be 0 again. Right, that would be the shortest it could take you if you didn't even cross the river. So let's go up to 100 seconds. All right, so I'm going to graph that. Let's see what that looks like. So you should notice there's this dot right here. What is that? You should ask yourself, what is that? And if you're confused, let's go ahead and let's do our table. Let's start at, why don't we start at 90 degrees, because that's where they, right, 90 degrees, he's walking, basically, it's taking him 24 seconds. So let's just see what that looks like. So notice at 90 degrees, it's taking him 24 seconds, right? Okay. Now, he can't go 90 degrees on the second. Well, I guess he could. But more than likely, the river is going to carry him to a different angle, so it's probably not going to be 40 seconds. I doubt he can stay along that river, cross that river at a complete 90-degree angle. Okay, but if he decides to walk the bridge, 24 seconds. Okay, and so you can just kind of see what's happening as his angle is getting smaller and smaller and smaller. And the same thing's going to happen the other direction too. As his angle gets bigger and bigger and bigger, it's very symmetrical. It was very similar to like a parabola. Right? So as this angle gets bigger and bigger and bigger. So basically what ends up happening is we have this graph. Let me get rid of my calculator here. We'll let this be theta. And at 90 degrees, his time, so f of theta, which is really time, is 24 seconds. But there's this, there's this second piece that is also giving us this time at like 40 seconds. But we know that that can't be possible. So we leave a hole there, and the rest of the graph looks something like this. And you can put in times there if you want to. It's up to you guys.